Hi guys, welcome back to our ongoing discussion of protein folding and stability. Hopefully in the last section, you were able to develop something of a pretty good feeling or a sense for why it is folded protein structures are stable, right? We talked a bit about cooperativity, how that cooperativity is explained, this idea of these connected interactions leading to this sort of single unit kind of behavior that well-folded globular proteins display. The fact that it's all about the energetics. It's all about this balance between the stabilizing interactions, compensating for the loss of configurational entropy, the release of the ordered water, helping reduce that entropic barrier, right? And the weak interactions made stronger by virtue of their being linked into this polymer, helping hold this structure tipped just across that energetic balance, 20, 30, 40, 50 kilojoules per mole into a stable structure. Okay, another way of thinking about this, right, another way to put it, is the idea that the folding of most globular proteins, right, is thermodynamically driven. And still another way to think about it, another way to state it, is that folding is under thermodynamic control, right? That all you really need to know in order to understand how a protein folds or why a protein folds is the idea that the thermodynamics of the system, the polypeptide and water, dictate that the energetic balance of the weak interactions, coupled weak interactions, release of ordered water, loss configurational entropy is all balanced in a way that it's the thermodynamics of that system that drive that protein into that collapsed, highly structured and folded state, right? It's a powerful idea. It's a really simplifying idea. It sort of implies that you don't, all the messy details in there you don't really need to worry about. You just know something about the thermodynamics of that polypeptide and you're good. You can sort of understand to a first approximation how and why proteins fold. And like I said, it's a simplifying idea. This idea is basically the one for which Anfinsen won the Nobel Prize, right, in the 1970s for his studies on protein folding, right? And this was great. And then, and not long after Amundsen did all of his work, another sort of famous protein or biochemist came along and kind of wrecked the party, right? Everybody's like, oh, this problem is just thermodynamics. That's all we have to think about. And then a man by the name of Cyrus Leventhal came along and said, well, wait. You know, maybe this isn't quite as simple as the thermodynamic control hypothesis suggests. And he did what was essentially a cocktail napkin derivation to make this point. And he even went back and said, well, let's just, even if we just take the protein that Amundsen had worked on, right? If we just take RNase A, what Leventhal pointed out is that RNase A can fold from a completely non-native state to the native state, can basically do this reaction, unfolded to the native state, right, in a few seconds, right? Okay, why is that a big deal, right? Like, okay, so it folds fast, right? Here's why that's a big deal from the point of view of, do we really understand how a protein folds? All right, so we take RNase, right? And we're saying, okay, well, we rounded it off before, right? We said it has, I was going to say it's approximately, let's say 100 amino acids, right? It's 124, but remember we rounded it off before for that quick calculation. That'll work again here pretty well. So let's assume, kind of like we did before, a limited conformational space for the protein. Let's assume, let's say 10 conformations, right? for each amino acid are available, right? That's a stupid undersimplification. There are undoubtedly more available for most of the amino acids in a polypeptide, but let's just say that's what's available. And so in the unfolded state, there are only 10 configurations for each amino acid, right? So what those two ideas would mean is that the total conformational space available to the unfolded protein sort of in the unfolded state would be something like 10 to the 100 conformations available, right? Okay, so that's a lot. All right, but now let's say, let's assume that the protein can sample, let's say RNAs can sample that configurate each configuration, right? In about a tenth of a picosecond, right? That's sort of in the ballpark of sort of bond oscillation frequency, 100 femtoseconds. It's really freaking fast, which would mean that the protein could sample conformational space at about 10 to the 13 conformations per second. Like, that's pretty good. That's pretty fast, right? All right. Well, if that's true, all those ideas would now imply that for the protein to fold, if it sampled conformational space exhaustively, sampled every possible configuration, looking for those ones that were really the stabilizing interactions that gave you a folded protein, that would mean the protein needed to sample 10 to the 100 conformations at 10 to the 13 conformations per second, which would be about 10 to the 87 seconds to fold. All right. Okay, here's the problem, right? Two problems. One, the sort of outer bound for what people have estimated the age of the universe to be, it's probably less than this, but it's sort of like on the outer bound, is somewhere in the range of 20 billion years, which is in the range of 6 times 10 to the 17 seconds. See the problem? If it took a protein 10 to the 87 seconds to fold, no protein ever in existence could have ever folded, because it was many, many, many factors of universes before you could ever fold a polypeptide. In addition, we know that can't be the case because experimentally, Amundsen and others could demonstrate that RNase A could fold in a few seconds. So it's not possible for a protein to fold by exhaustive search, complete and exhaustive search of conformational space. That search has to be massively more optimized and efficient to get a protein like RNase to fold in a matter of a few seconds. All right. So if you don't fold by random or by exhaustive conformational search, how do you fold, right? The thermodynamics of the fact that something folds don't explain that. Remember, thermodynamics only tells you the energetic difference and some of the component of that energetic difference between two states, state one and state two. It doesn't tell you anything about how you get there. And folding is one of those things, you really want to understand it, you got to know how you get there, right? So the path taken is going to make a big difference in our real understanding of protein folding. Well, how do you solve that problem? How do you solve this massive conformational space problem? You've got to do something that collapses that search, right? You got to reduce that search time. Okay, well, if you think back to that toy model from the last lecture, remember my protein here, my 4 amino acid folding protein? This scheme, as I've drawn it, might give you a bit of a clue. What if this protein preferentially, almost always, maybe always, went this way, right? What if this protein almost always went this way first, right? Because the BC interaction, those are right near each other, right? So the entropic penalty, we've already paid a lot of it by putting them in a polymer together. They're right nearby. So the entropic penalty of getting those guys to form first is a whole lot lower than getting A and D to form first. So if they form first, that is then going to reduce the entropic penalty of forming A and D. And so we've got a specific sequence of events. The protein folds first by going this way, then by going here, and finally we're over here in a specific order of events, right? Now that should look like something maybe you've seen before, right? You think about things like metabolism. Step 1 goes to step 2, then goes to step 3, and they always go in that sequence. That, right, solution potentially to this problem, all right, is potentially what you could call a folding pathway, right? The idea being that in addition to proteins evolving to have an energetic balance that stabilizes the native state, those amino acids have been positioned in that polypeptide chain in such a way that there's a specific sequence of events, contact events, from the point of fully unfolded to the point of the native state that always happen the same way every time. That protein makes that first set first, then the next set next. And remember that cooperativity leads to that cascade. And so you don't have to exhaustively search because the order of events that lead to a folded state are prescribed in a specific way by that sequence of amino acids and the thermodynamics, right, of that polypeptide in solution. Local order leads to then this very specific sequence of interacting events that came to be called a folding pathway. Okay, the nice thing about that idea of a folding pathway is it fundamentally solves Levinthal's paradox in a really simple way, and that's great, right? The other thing, there's some other things about this idea of a folding pathway that's kind of cool, because the folding pathways suggest some other things that are also neat, right? So, or are consistent, I guess, with how proteins seem to fold, right? It's absolutely true. It has been shown to be true by lots and lots of studies that proteins absolutely do fold by this sort of progressive accumulation of structure, right? This fact that you have your unstructured, then you start seeing secondary structure, and then tertiary structure usually lags secondary structure. That smells a lot like an ordered sequence of molecular events, right? You can, in some cases, for some proteins, find things that look like sort of something that's ordered in between fully unfolded sort of random coil polypeptide in the native state, things like the molten globule intermediate you may have heard of before. In addition, the kinetic behavior of many folding reactions is incredibly reminiscent of simple chemical reactions. You can see kinetic behavior, transition state behavior, which we'll talk about later, that is very reminiscent of simple chemistry, right? And that sort of, again, reinforces this idea of a folding pathway. And this was great. And people went off in search of folding pathways. We're going to find the folding code, be able to predict how proteins fold by just characterizing folding pathways. This led to several decade-long search in how to describe protein folding pathways. And the problem is it just hadn't quite worked out that well, right? Even though some of these, there are things that are consistent with this idea, there are other things that are not, right? So one of those things that's not consistent is that fundamentally, people even recognize this very early on, is that proteins are not discrete chemical entities. They're not, you're not talking about, in a protein folding reaction, a simple like SN2 sort of organic chemical mechanism. You're swapping a couple of atoms, right? This is a far more complex problem. It's a polymer dynamics problem. So the degrees of freedom are massively more complex. So it's actually just kind of remarkable that any aspect of this process models something like a simple metabolic or chemical pathway. In addition, as people dug more and more and more and more, the existence of discrete folding pathways and intermediates seem to be elusive. In some cases, you'd see things, right? In other cases, similar proteins, you wouldn't see it at all, no intermediates at all, or there'd be sudden plethora of intermediates, right? And the slight changes in the folding conditions would make different intermediates appear or disappear. And that's just a hard thing to explain with simple folding pathways. Okay, so the resolution to this conceptual problem sort of came about as a result of work that sort of came from people coming at this problem from polymer chemistry or polymer physics, guys like Peter Wollenis, Ken Dill, and some others in the 1980s. And what these guys said is, wait a minute, stop with the simple chemical pathway idea. We've got to embrace some of the complexity of what we know has to be going on because it's a polymer dynamics problem. And they said, let's think about it this way. Let's think about that whole conformational space available to this polypeptide, and imagine a slightly different sort of conceptual framework. And they said, let's take all the possible configurations available to that polypeptide and map it out on a surface. Let's imagine like a plane, right? And in this space, this plane, all the configurational states available to the polypeptide are going to be represented, you know, at least in a conceptual way. And the width of this sort of space, right, is proportional to the entropy, right? So this is proportional to essentially the configurational entropy of the polypeptide. And then perpendicular to that plane, let's plot the contact energy. Essentially, you can think about this as sort of that stabilizing enthalpy that holds any given configuration together, right? So when you do that, you come up with this conceptual framework that looks like a landscape, right? So configurational entropy in this dimension, in the orthogonal dimension, you've got sort of stabilizing energy, right? It's a little more than just the enthalpy, but you think about it as the amount of internal energy that's stabilizing any given conformation. And right in the center, right, so on the outer edge out here, you've got the sort of the unfolded states of the polypeptide. In the center, you've got the native state, right? And you fold then by moving across this energy landscape through configurational space and down into the global free energy minimum where the native state is stable. That's cool. Now, if you look at that landscape as I've drawn it, or as it's drawn, this came from a review of Ken Dill's from some years ago. If you look at that particular landscape, right, it looks stupid, right? It's completely flat, right? Folding across this landscape would essentially be a random walk until you manage to somehow eventually, you know, wander your way around and then hit the free energy max. It's like a golf course, right? This is more or less an expression, a folding landscape expression of Saris-Leventhal's paradox, that a random search through conformational space would lead to this insanely long, nearly random search to find the native state. But everything we've talked about up to this point, you know, means that proteins don't fold that way, right? We know that proteins, when they fold, by virtue of the fact that the local contacts are linked to each other thermodynamically, and the first set of contacts make the next set of contacts easier, that experimental observation of cooperativity in folding means that the folding landscape has to be sloped, right? So this outer edge again, where we've got the unfolded state out here, as those contacts begin to be made, right, they make the next set easier to be made, right? And that's worth some stabilizing free energy, which means it has to drop down that orthogonal dimension. So the landscape has to be sloped. Folding then in this sort of landscape parlance then becomes excursions across these free energy hypersurfaces with a natural thermodynamic drive down to the global free energy minimum at the center of the landscape, right? And now the cool thing about this landscape framework point of view, at least as a way to conceptualize some of the weird things that show up in protein folding behavior, it's now trivial to explain how the same protein can populate at the same time two different folding pathways or behaviors. It's a matter of different subsets of that unfolding ensemble out here going down, say, one trajectory or down another trajectory, in this case, forming some sort of a folding intermediate on its way, right? So it's just a matter of where you start on the landscape in terms of how the overall folding behavior tracks, right? Okay, so that's great, right? So that's now a fairly simple sort of idea to help explain some of the complexities in folding that don't require tying yourselves in knots around simple chemical metaphors of pathways. But the question now is, well, but there's still these observations where folding pathways make so much sense conceptually. You can explain things really simply, and the kinetic behavior in many cases things look an awful lot like a simple chemical transformation, or at least they act that way kinetically. So the question then is, do we have to give completely up on this idea of writing down folding reactions the way I tend to write them down, right? With these sort of like, descriptions like this, that's a folding pathway, right? Or this to an intermediate to native state. Do we have to quit doing that, right? If it's fundamentally an incorrect representation. And what I'm going to argue is that no, of course we don't have to give up on that idea if we keep something in mind. Remember, somewhat more correct conceptual viewpoint of this polymer dynamics problem is this collapse down this folding landscape, right? This movement through these folding funnels, right? And so up here at the top, we of course we'd have the unfolded state. And as we move down the landscape, we're shedding configurational entropy, we're gaining stabilizing internal free energy until we get down here to the native state, right? But if you think about it, you can imagine averaging at any given sort of contour level across this landscape, right? So that what you're looking at when you write down a pathway like this, up here at the top, you're looking at an ensemble average of the states available to in the unfolded state or the unfolded ensemble. Same with these different intermediates. So what I would argue, and I think a lot of people would argue, it's completely permissible to write down a folding pathway this way, right? Where each of these symbols now represents a major, well-represented feature of this folding free energy landscape, right? That when an intermediate is sort of detectable, that's the feature, sort of a property of all the contour levels at that energy level of the folding landscape. But what you just have to keep in mind is when you write things down this way, these are not, with the possible exception of this guy, these are not discrete species. They're still ensembles of conformational states that get narrower and narrower as you go down, but they still, when you write down a symbol, it's sort of you're writing down something that represents the average properties of an ensemble of conformations. As long as you keep that in mind, you won't get yourself in trouble. Okay, so with that sort of basic idea, right, you can sort of link up this sort of collapse of conformational space into the native state and even deal with a certain amount of the sort of messy complexity that simple chemical transformation models like pathways can't handle, but you can still retain some of the utility and simplicity of writing them down this way that lets you discuss things in a simple way, right? Which is a good thing. Okay, so next time we're going to discuss a little bit more sort of overview of how we think folding works, and I'm going to leave you with a few more thoughts about how folding works in the cell.